This is the Saturn V rocket, and it's the most powerful machine that man has ever built. It's a really good example as well of Newton's third law. It's a really good example of an explosion. The rocket throws out extremely hot gas from the exhaust at the back here, and that extremely hot gas actually pushes the rocket forward. So action is that the rocket pushes on extremely hot gases, and the reaction is that the extremely hot gases pushes on the rocket, and that is the thrust that pushes the rocket forward. 30 million newtons of thrust. So this video we're going to talk about Newton's third law, which is often called the law of conservation of momentum. We're going to consider some examples of that, and we're going to start by considering collisions. Collisions, like every example of the law of conservation of momentum, involve considering the momentum before and the momentum afterwards. And it's a law of conservation, so that means that the momentum before is going to be equal to the momentum afterwards. So I'm going to take my car, this is A-Dog, we've met before, and I'm going to drive it into the back of Daffodil, the smaller car. The mass of A-Dog is 1500 kilograms, and the velocity I'm going to drive is 30 meters per second, about 60 miles an hour. Daffodil is a smaller mass, 1200 kilograms, and it's stationary, so it's got 0 meters per second velocity. So I need to calculate the momentum beforehand. So I hope you remember the equation for momentum is P equals m times v. Momentum is mass times velocity. So A-Dog, mass 1500 kilograms times by its velocity 30, and I'm going to add up the total momentum in the whole system. So although I know this momentum is going to be 0, I'm just going to write it in for good measure. The momentum of Daffodil is its mass times by its velocity. So now I'm going to go for the calculator, and 1500 times 30 plus 1200 times 0 equals 45,000, and I hope you remember the unit, kilograms meters per second. Okay, now that is going to be the same momentum afterwards as it is before the collision. 45,000 kilogram meters per second. But of course some things happened, and they're no longer travelling on their own. They're actually travelling as one combined mass. So if we want to work out what is the velocity of that combined mass, well, then we're going to need to add the two masses together, and because we've got only one unknown, we can work out the velocity. If I rearrange that for v, I get v equals p over m. So the combined mass then, the total mass if you like, is 1500 plus 1200, which is 2700 kilograms. Let's put that on. Go for the calculator now. So write out what I'm going to put in first. So momentum 45,000 divided by 2700 is 16.6 recurring, or 16.7 meters per second. Okay, so that's pretty simple really once you know how. I'm going to try a different situation now. We're going to try a situation where the two cars are moving. So here's A-Dog again, and I'm going to drive with the same speed, same velocity in that direction, but this time Daffodil is going to drive towards A-Dog with a higher velocity. So once more I need to work out the momentum beforehand. Remember, momentum is mass times velocity. So the first one here, momentum is 1500 times by 30, it's the same as last time. And I'm going to work out the total, but I need to remember this velocity is in the opposite direction to this velocity. So I need to actually take away this momentum here. So 1200 times by 50. You could just treat that as minus 50 and that as a plus, and you'll still get the same result. Again, going for our scientific calculator, 1500 times 30, take away 1200 times 50, minus 15,000 kilogram meters per second. So now you see that overall momentum when we have the head-on collision is 15,000 kilogram meters per second in this direction. Okay, so afterwards our momentum is minus 15,000 kilogram meters per second. And again, I can work out the velocity in that direction is P divided by M. It's now one combined mass, so once more the total mass is 1500, add 1200 is 2700 kilograms. Input the numbers, minus 15,000 divided by 2700 is equal to, divide by 2700, 5.5 recurring, or 5.56 meters per second. That's the three significant figures. Well, that's collisions. I told you that Newton's law applies also to explosions, and we'll go on to that in just a moment. I first of all just want to show you this, and this is telling us a slightly shorter cut, if you like. If you have a good understanding of that, then this is a good way to save yourself time in the exam. We can say that the momentum of the first car initially, the first object initially, added to the momentum of the second car initially, is equal to the two masses added together times by the velocity. Now what you could do is just input all the data that you know and rearrange for velocity, and you would be able to calculate that velocity straight away. I would just say, as long as you can identify this is the mass of the first one, the initial velocity of the first one, mass of the second, initial velocity of the second, the two masses added together, and the final velocity of the combined object. It's a nice, useful shortcut. I think, though, it's useful to go through step by step to make sure you understand, in case you get into trouble in the exam, that understanding will help you. So then, another situation is an explosion. So we're going to need some ice to demonstrate this, and we're going to need our assistant from a video a while ago. Here's Snowbird, and he's on his ice skates again. He's going to be joined by a koala called Cuddles. Now, Snowbird is actually going to push on Cuddles, and in doing so, Cuddles therefore pushes back on Snowbird. Their action has an equal and opposite reaction. So we've got a Newton's third law. We're going to need to work out what Snowbird's velocity is. So we need some data. We need Snowbird's mass. He's a 5 kilogram bird, and Cuddles is a 10 kilogram bear. He's a plump bear. The velocity that Cuddles moves off in that direction is 5 meters per second. And it's still going to be a situation where we're going to consider the momentum beforehand and use that to calculate the velocity of Snowbird afterwards. So beforehand, well, they're both stationary. So that's a nice easy one. The momentum beforehand is 0 kilogram meters per second. So we know afterwards the momentum, the total momentum, even though they're both moving, the total momentum in the system adds up to 0 kilogram meters per second. So what we're saying then is that Cuddles' momentum is equal and opposite to Snowbird's momentum. So if we work out Cuddle's momentum, (10 kilograms times 5 meters per second), 50 kilogram meters per second, then we know that Snowbird's momentum is just minus 50 kilogram meters per second. They add up to make a total of 0. So once more, we know everything we need to be able to solve the equation for velocity. Rearrange for v and you get P over m. You get minus 50 divided by his mass is 5 kilograms. Don't need the calculator for that one. That's minus 10 meters per second. So Snowbird moves off with 10 meters per second in that direction. Okay, now there is a little bit of a shortcut for this one as well, that I'll give you that same health warning. If you understand it well, then actually inputting the mass of the first one and the velocity of the first one and the mass of the second one will leave you with an equation with just one unknown that you can resolve to calculate v. A nice shortcut. Don't forget to click down here to subscribe to my channel so that you don't miss out on any other videos, and if you found this helpful, maybe your friends will as well, so go ahead and share them for me.